Good morning, everyone. I'll be talking on fabrication process today. Thanks to Savita Engineering College for giving me an opportunity to share some of my work here. I learned most of fabrication or whatever I know a little from Professor Shankar Kumar Selvaraja when I was a postdoc at IASC. I thank Professor Shankar and I also thank Dr. Lima, Assistant Professor at VIT, from whom I have learned a little about fabrication. I'm also going to show some of my results uh, on fabrication, and I'll show some of the results of me and Anup, a postgraduate student at IISc. So this is how I have designed the talk today. I thought I'll introduce the audience a little briefly about clean room and then the fabrication process inside clean room, starting with the deposition of desired materials like thin film deposition, and then designing or patterning, and then going for a lithographic process to develop devices and the structures out of lithography are not permanent. So in order to make a pattern transfer effectively onto the substrate, we'll have to carry out etching and then cleaning. These are the set of processes that we will be probably looking at today very briefly. And then I'll end the talk with one of my rather by showing you a set of beams, silicon nitride beams that we have developed at IAC. So to start with, why do we need clean room? We need clean room because we don't want the devices to have defects or dust particles. We need extremely clean ambience in order to develop defect-free, dust-free devices. And the level of cleanliness that we are talking about is per feet cube. We are talking about 100 particles, 1,000 particles. Accordingly, you can see classification of clean rooms based on the number of particles per feet cube here, or based on the number of particles per meter cube of air. So that is the level of cleanliness we expect when we have our devices developed. And in order to maintain that inside a clean room, we ourselves are one of the biggest sources of contamination. We need to have personal protective equipments like what you see here in this photograph that people are wearing. And in addition to it, in order to maintain your safety, you also need special personal protective equipments when you work inside chemical benches, fume hoods. You need to probably wear chemical resistant gloves and things like that. And why do you see this room to be yellowish? Because you do not want, especially when you carry out lithography, you do not want your material to be exposed to the light. So that's why you need a special cover. You maintain some kind of a photosensitive ambience inside the clean room, especially when we have a lithography bay or lithography bench. And inside clean room, we have special equipments like, there need to be a special area to develop materials, to develop thin films of desired size, of desired thickness, from a desired process. So you need to have equipments that concern thin film deposition, and then you need to have equipments that characterize certain properties, not all properties, but certain important properties inside clean room. Suppose you are working on transistors, you need to know what kind of resistivity your substrate has, or what kind of resistivity your pattern has, or whether, especially when you have transistors, you will have, say, a lot of metals, metal patterns, interconnects to be, we will pattern all of them. So we need to make sure that metals don't diffuse into one of those layers, because when we do develop devices like transistors, we will have number of layers, lithographic layers to be patterned, a number of layers to be developed, and especially the metal layers should not come together to short circuit, so they should not diffuse. So in order to do that, you need to know what is the resistivity that you're working on before and after a particular deposition, or before and after a particular patterning. And after that, you also need to know, suppose you are developing thin film structures like, say, cantilevers or beams, and you need them you need them for a particular reason, and they should have a particular thickness. And you need to make sure whether your process has given that particular thickness or not. Whether, especially after processes like etching, you need to check whether your material is in there or not. So you need to measure thickness. And similarly, you also need to look at the patterns, like optically, to check not the morphology per se, but at least features. To identify features, you need to have optical microscopes and sometimes electron microscopes too. These are the kind of characterization you may want to do on the thin film that you have developed, or on the patterns that you have developed. And then you have a special equipments to do lithography, and you also have to develop features, at least temporary features on top of layers, which you will be seeing in some time. And then you have specific area for etching alone, and we have two types of etching there, dry etching and wet etching, and why we need to etch. We will see all that in detail, but this is kind of information you have, or this is the kind of equipments you have, you can expect typically inside a clean room. And why do we need all of this? Because when you say develop thin films for a particular reason, which you will be seeing in some more slides also, the properties are tremendously modified as you go down this size. What, for instance, this image shows is, when you have a small cube of this dimension, say 1 centimeter, your surface area is this and your volume is this. So when you compare the surface area to volume ratio, your surface to volume ratio, you have a surface to volume ratio of 6:1. But as you cut this into multiple number of pieces, you're increasing more surface here. Your surface area to volume becomes more, because of which you can see properties of this kind. Suppose you're looking at density of states, which I think you must have heard in your physics classes. What quantization typically, as you reduce the size of particles, or as you reduce the size of thin films, when you go down the size, what it does, considering only the electronic properties matter now, what it does is the level of quantization changes the density of states. If you look at bulk, which is of this size, the way your density of states, the profile of your density of states is different compared to when you have a very small nanoparticle, or a thin film, or a one-dimensional wire. Which means, suppose you look at a luminescence, say a luminescence spectrum, the material, say you are looking at gold nanoparticle, The luminescence of a gold nanoparticle will be, for bulk will be different, and for a for a nanoparticle will be different. So this confinement gives rise to exotic properties and which can be exploited in newer technologies, is what this slide tells you. Also, okay, other than the properties as you go down the size, typically in the industry, uh, as far as the design rule is concerned, the kind of components that we look at as per say 2013 here in the state, the smallest component can be, or smallest transistor say in this case, can be 10 nanometer or less than that. We have reached a state of art of say 7 nanometers, and people are looking into sub nanometer levels or dimensions of devices, which is also what kind of Moore's law says, that as time increases, the number of transistors in a microprocessor would be more than this number, which means the number of transistors, if they go up, the size of transistors should be extremely small. So one of the reasons that we go for fabrication is fabrication of new devices. Small devices means fabrication with exotic properties, enhanced properties, and also very small sizes. From the days of big computer to tablets today, from the days of big cell phones to the kind of smartphones we have, speaks of this. And that also tells us the need for finer fabrication. When we look at finer fabrication, we have to think of materials, because we are actually patterning different kinds of materials and making them thinner and making them creating fine features on a material. If you look at material, you have different types of material. You have amorphous materials, you have crystalline materials, and even in crystalline materials, when you say amorphous, what we say is we don't consider arrangement of, we don't have an orderly arrangement of atoms. Why is this important? Which we will see in a few slides down the line now. And we have crystalline materials, which means we have a specific orderly arrangement of atoms like this, but then we have boundaries, which means we have polycrystalline material. Suppose you take copper. Copper has a particular arrangement of atoms in here, and then when it is separated by a boundary, you see a particular fashion of arrangement of the same copper here. But we have single crystal materials, which means you all through the material you will have only one particular orientation of atoms, and this is going to give you enhanced properties. What this shows here is a transmission electron image or micrograph of a strontium titanate crystal deposited on top of another metal oxide here, complex metal oxide here. What it says is you still have no orderly arrangement of STO in one pattern. You can see STO or strontium titanate as one pattern here. How is it going to be useful? We will see in few slides. So there is so we need to actually deposit desired materials, and we need to also deposit them to desired thicknesses, and we also need to deposit them with a particular orientation. By orientation, it should have say if you understand a cube, probably we as an example I'm saying we have to deposit materials in only one particular axis, and apparently that's going to give us a lot of enhanced properties. Moving on to the next slide, this tells about thin films of say 1 to 100 nanometers being used as MOSFETs, field effect transistors. What this says is when you have a strained material and when you don't have a strained material, so basically we use silicon here. In one case the silicon is strained and another case silicon is not strained, and this is a typical there are different layers of materials that need to be deposited and etched out, patterned and etched out, which we will see later. I'm just telling you the need or importance of such oriented or strained materials probably here. You see a different, totally altogether an enhanced property in the mobility. If you understand what mobility is in terms of transistor properties, we look at very different mobilities when your silicon is strained compared to an unstrained silicon. This is because when the crystal is strained or when the lattice is stretched out, we can have defects which can kill the property, or sometimes it can enhance the property. So we need to know so for this reason we need to know something about little about materials and more about material deposition, materials growth, which is also a part of fabrication. And here is just an example of how these crystal structure is when it is strained, how is it relaxing, and what is it giving rise to when it is stretched. It is stretched this way by the formation of an extra layer of or extra line of atoms. These are called dislocations, misfit dislocations. This is a defect in a crystal. And now similarly, if you look at the same feature size, a few nanometer thin films, they can be used in vertical cavity surface emitting lasers. If you know what VCSELs are, that's where we use what is called epitaxial thin films. What is epitaxial thin films? Which means they are oriented thin films in only one particular axis, for which we need to know a little bit about crystal structure, but that doesn't matter now. What we are trying to say here is we are going to have a stack of this. We are going to have a layer of gallium arsenide, say, and then we are going to have some kind of layers deposited on top of it, few of them etched, of new layers to be deposited of these kind of dimensions. We are talking about 10 nanometer or few nanometer thicknesses of different stacks, where we have indium arsenide in between and then gallium arsenide, indium arsenide stacks. And how are we going to deposit them? And what is this going to do? We have thin as 80 angstrom layers can be deposited, and these also can be epitaxially oriented. And what is this going to give? It's going to give us an enhanced property. This cavity is going to give what it is going to give is a lasing action, which means this kind of a stack with gallium arsenide as a substrate, and then you have a stack of this kind of dimensions, and it with indium arsenide, when it is stacked, you can actually see an edge emission. That means from the edges you can see light coming out of particular. So when you pump it like this, which means when you shine light across of a particular wavelength in this fashion, you will get a different colored light, or depending on the stack, depending on the material, depending on the gap, you will get a different kind of an emission here, and that can be powerful enough to use as a laser. That's what it means. And all of these can be possible if we know an idea of fabrication. And similarly, you have varied structures, like they are called microfluidic cantilevers. If we can fabricate these kind of fixed beams, they are also called cantilevers, and this is a recent report, and if you can actually deposit a microfluidic channel and you can put a material on top of it and shine it with quantum cascade laser, which is famously called as QCL, what you can see is this structure. You do not need a spectroscopic measurement to know what material you have added. Instead, the deflection of this cantilever alone can tell you what material is present, which means we can do a spectroscopic measurement with just a cantilever without actually a spectrometer, or without actually very high-end equipment, without having a very high-end equipment. This happens because of this particular formula over here, because frequency is given or directly proportional to the spring constant and the mass, and the moment you are going to add a different mass over here, which is on top of the cantilever that you have, bimetallic cantilever, and then you have a small liquid put on top of it, you can actually calculate from this what kind of material it is, by the way, if you map the actuation of this cantilever. So which means this kind of a this can be used as a spectroscopic tool to identify explosives, to identify chemicals near a plant. It can be a very inexpensive way of measuring it, measuring chemicals. It can be a chemical sensor, infrared sensor, and so on and so forth. So which means all of this can be made, new kind of devices itself can be made if we know what material, first of all we need to know the material and also the kind of fabrication that is involved to make it a feasible device. In this case, a cantilever can be used as an infrared spectroscopy, to do carry out an infrared spectroscopy, thereby detecting molecules or chemicals. This is one of my work with Dr. Lima here. We were able to use silicon cantilever. We didn't fabricate as such. We were able to use silicon cantilever as a photothermal actuator, which means if you shine light on this material, which is a semiconductor metal oxide, at a particular temperature, it suddenly shows up huge deflection, which can be used for multiple purposes. For strain gauges, it can be used in multiple things. So fabrication of materials is very important for newer type of technology, for newer materials development, and to make newer devices. Another example of a light emitting diode here, and you can see the number of different layers that need to be deposited, a number of complex process that is involved in making. We will get to there very slowly, and if we do all these things in a very controlled manner, if you know that you are dealing with 60 nanometers, 20 nanometers, 2 nanometers, 3 nanometers, and if you know the precision, if you are precise enough to get there, we can make high performing devices. So to review so far, what we have done is, from bulk single crystals to thin films and to lower dimensional nanostructures, we know the properties of the material changes because of surface to volume ratio, and all of these can be used from the materials front as well as from the device front to make newer devices with better performance and varied properties, and for which we need to know we need to have an idea on crystal growth, materials, and things like that. And for which we need to know about vacuum systems, because most of the fabrication facilities always use vacuum systems. be it for thin film deposition or patterning or for etching, we always use vacuum systems. And they are very sensitive to all these processes that we've discussed so far are very sensitive to environment. So which means we need to usually protect all of our carry out all of these processes in a very controlled ambience. That's why we need vacuum systems. If you know typical vacuum system, all of these are typical vacuum system, right from desiccator like this to a very hi-fi chamber like this. What we actually do is we are reducing the number of air particles inside such a chamber by sucking out the air. And the kind of vacuum that we are dealing with depends, and it can vary from the type of pump that we use. So we need, for thin films, we work at purity levels of 99.9999%, and that which means that much of air is removed, which means every 100 million air molecules present in the chamber when open to room air, all of these will be removed except for one in vacuum, which means it provides an extremely clean environment and high purity. We need to work with very high purity source material. As I said, if you have more molecules, then you will have higher pressure and you do not need it, which means, considering the temperature is constant, you have pressure is the amount of gas molecules which are present inside the chamber. So if air is removed, we measure how much air remains by measuring the pressure. So there are different units for measuring pressure. Some of them are torr and Pascal. A normal room has a pressure of 760 torr. As we remove it, the pressure will drop. If 99% of air is removed, the pressure will drop to 7.6 torr, which means you can see the number of air molecules or molecules in general here, and you have only nitrogen here in a closed chamber. The oxygen or carbon dioxide are much reduced or less. So if you compare this high vacuum that we are using to deposit thin films, as we compare it to outer space, so at International Space Station, the level of pressure is 10 power minus torr, and the kind of vacuum systems that we work is 10 power minus 7 torr, which means establishing such a vacuum needs hi-fi pumps. We need a very very good sealed chamber with solid enclosure. And we need to have a high vacuum gasket to make it vacuum tight. Air molecules should not leak. The pressure should not increase. We need to use one of the typical materials that are used in as a gasket material is a vacuum compatible rubber. Quickly, if we just go through the kind of pumps that are usually used. In general, there are three categories. One is called a positive displacement pump, which just pushes air out of the chamber. And then you have momentum transfer pumps, which means they just bounce air molecules out of the chamber. And then there are entrapment pumps, which means they trap or freeze air molecules to remove them out of the chamber. All three of them to ultimately reduce the pressure inside the chamber, but by the way they do it is different. So when you deal with the specific pumps, you have mechanical pumps which do not actually suck out air, but they push volumes of air out so if you have it entering here, a small particle, it just goes out by the blades pushing it out of the chamber. These pumps cannot be used less than 100 millitorr. They are usually called backing pump or rough pump. They should be used if you are using a very high vacuum or a low pressure chamber, very high vacuum like 10 power minus 7 or minus 8. We can't let them work alone. We also need the help of vacuum roughing pump or backing pump like these pumps. So once we start using this, it takes us to a particular level of vacuum, and after that we need to switch to another pump which starts sucking air from that level, say 10 power minus 2 torr to further 10 power minus 5 to 10 power minus 7. So until then, to establish to that level, we need to use mechanical pumps. If you consider pressure versus pumping speed, this is how the pumping speed relates to pressure. After a particular pressure, it doesn't pump at all. It becomes saturated here. And next pump is a turbo pump, which is mostly used in, of course, backing pump is also used in deposition systems. Turbo pumps are very heavily used in deposition systems and also in etching systems. We use turbo because mechanical pump has a limitation. It can only go to a certain limit, which is say 100 millitorr. In turbo, we have high-speed fans rotating like this, turbine blades, and the speeds at which they move are compared to the speeds of the gas molecules, and because of which when the air molecules hits one of these blades, they bounce off outside the chamber into the pump, and they have the capability of sustaining very high compression ratio, that is the ratio of gas pressure at the output to that of the at the input. And so as I said, mechanical pump can be used as both a rough pump and a backing pump for a turbo pump. And the revolution per minute in a typical turbo pump can be very high, like 50,000, and an RPM of a mechanical pump can be less than 5,000. When you compare that of a helicopter's RPM, it is 400 to 500. And we need to make sure that there are no leaks in the system before we use, and there should not be any degassing or outgassing inside the chamber. These can literally deteriorate the processes that we are aiming for or the quality of the films that we are looking at. And then comes cryogenic pumps. They can be, the cryo means very low temperature. We use typically helium as the coolant, which can go up to minus 258 degrees Celsius or 15 Kelvin. The plus point of this is cryo pumps is that it can go up to 10 power minus 8 torr. It also needs a mechanical pump for, as a rough pump as well as a backing pump. The saturation limit can literally kill the working of a cryo pump, which means if all of these air molecules condense on top of the baffle or fin, when it cannot further add more trapped air molecules, it cannot work as efficiently as it used to. So it needs to be dried up, it needs to be evaporated, then the pump is ready to be used. What it actually does is molecules condensing on these baffles or metal fins, thereby making the chamber quite sealed. Thereby making the chamber very high vacuum. Usually this is one of the limitations, but heated nitrogen gas can be used to evaporate the trapped air molecules. Once it is done, the pump can be used. So to review, we just looked at different kinds of pumps. Why should pumps be used? These pumps, first of all, pumps are very important to perform both deposition. All kinds of equipments need pumps, and vacuum pumps. We saw about mechanical pump, turbo pump, and cryo pump. And then comes the deposition technique as such, the thin film deposition techniques. Typically, people use for fabrication processes, people use physical vapor deposition, thermal evaporation, and sputtering to deposit electrodes, to deposit metals for different reasons. And then chemical vapor deposition for typically deposit some silicon nitrides and oxides like titania And then pulsed laser deposition to really make conformal epitaxial films of um, exotic oxides for developing heterostructures or to develop modulators. We need pulse laser deposition. So broadly, thin film depositions can be classified as physical methods and chemical methods. We can deposit materials like metals, insulators, semiconductors, and these thicknesses of materials that we are looking at can vary from 5 nanometer to 250 nanometer. And if you look at thin film deposition, physical methods alone, uh, we have chemical vapor deposition, PVD, and then which is thermal evaporation, electron beam evaporation and sputtering, and then you have atomic layer deposition, then you have pulse layer deposition, then molecular beam epitaxy. In addition to it, you have ball milling, dry etching. These are top-down approaches, where these are bottom-up approaches. And then you have similarly again sol gel pyrolysis in the chemical method and chemical etching another method. We won't probably use much of though sol gel is a very favored technique to deposit certain films. These don't involve a lot of vacuum deposition systems like equipments that go up to say 10 power minus 7 torr or things like that. So if you look at say physical vapor deposition, we require very high source materials, pure materials, and we need a very high vacuum chamber, and we need to have a very good substrate. What it requires is an environment of 10 power minus 6 torr, which means so much of air should be taken out of the chamber. So one of those techniques is thermal evaporation, where you just use heat to evaporate a very high pure source. Say if you have a boat and you put your material on top of it, a very pure material on top of it, make sure that it heats up, so it starts evaporating, and so you need to make sure that there are very less atoms inside the vacuum chamber. So once the material is evaporated, it just goes and hits on the surface of the substrate to form thin film. So all these are a part of thermal evaporation setup. You need to have a proper gasket, you need to have a proper chamber, you need to have both backing pump and a turbo pump. Typically, boat material that is used is tungsten, and I have given a reason here as to why it is used. So this is a process called resistive heating, and you evaporate a material which is placed on top of it, and when you have a substrate, once it evaporates, it goes, hits the substrate and forms thin film. That's where you have a substrate holder. And then this is the same thing here again, like how the tungsten boat is clamped, and you send electric current over here. You have a crystal sensor. Why is it a crystal sensor? It senses it gives us an idea of how thick is the film. So whatever amount of material that is getting deposited here will also get deposited here. We can't measure the thickness over here, but this is programmed in such a way, once it reaches a desired thickness, the evaporation will stop. That's how it is. Crystal monitor sensor works. It just stops the flow of current. This is how a typical chamber looks like. Next thing is sputtering. Again, you use either a plasma to sputter. Sputter is again a very physical process. It removes atoms. So here is how it works. So you need to make sure that the vacuum is 10 power minus 6. That's a kind of vacuum that we work with, which means it also requires both mechanical pump and a turbo pump. What it means is you start with 10 power minus 6 torr or pressure 10 power 6. Then a small amount of say argon gas is leaked inside the chamber. Once argon gas is leaked, it forms plasma, which means actually you have electrode, you are deliberately creating plasma of the inert gas. And so because it is inert, it will not result in unwanted chemical reactions during this sputtering. When argon is in the chamber, you apply a negative voltage to the target, which is here. This voltage will be sufficient enough to remove atoms, remove electron from the argon atoms close to the target. So argon becomes ionized and positively charged. These ions strike the target at very high speeds, which is here. And because of this, they physically knock off the individual atoms of the target, and which because of this fly towards the substrate over here and get deposited. This is the principle behind sputtering. So why do we need physical vapor deposition in some case, and why do we need chemical vapor deposition in some case? We need physical vapor deposition because they are highly directional, which means you have a critical path defined for the molecules. Most of the times it's towards the substrate and it deposits exactly on the surface of the material. But the problem is it can give rise to non-conformal deposition, which is sometimes good and sometimes bad, which means it may not be smooth throughout here. It can give rise to a lot of contours and it can also give rise to trenches. It is not conformal. Whereas in chemical vapor deposition, though the direction is not unidirectional, it can be lateral as well. It can give you a very conformal film, which means everywhere you can get a very uniform conformal film. Coming to say chemical vapor deposition. Okay, sorry. You have CVD equipment described here. So you have different lines of gases that go through. You have a precursor, sometimes it's solid, sometimes it's liquid. And then you have a chamber, which is kind of a furnace or a heater. You have a small substrate holder. And then you have a vent valve. Here also you use different kinds of at least two different kinds of pumps. But you can also have an atmospheric pressure chemical vapor deposition equipment where we do not need a turbo pump at all. So it depends on what material you are depositing, what is the kind of precursor material it is going to be, and how harmful or harmless the whole process is going to be, and depending on which you can either design very low pressure equipment or an equipment that functions in atmospheric pressure as well. In chemical vapor deposition, you have a substrate which is placed under vacuum like this here, and the source gases mostly in the gaseous state are pumped inside a reactor or a chamber, or it's just a furnace. These gases react with the surface of the substrate to form thin films. You can use external stimulus like heat and plasma to initiate or propagate the reaction. And then the gaseous byproducts that are that result out of this process should be pumped out. And in order to stop the deposition, you need to stop the heating source, gas flow, and then turn off the pump. So it's an elaborate process. Once the deposition is complete, you should pump, in all the cases, you should pump the chamber down, remove the sample. And once the chamber is pumped down, sample is removed, you need to pump it again. There are different types of CVD, and like metal organic chemical vapor deposition, plasma enhanced chemical vapor deposition. There are so many different types of chemical vapor deposition. These are some of the reactions that happen inside the chemical reactions that happen inside the chamber before it forms the films. Again, these are explained in detail here, like how molecules come adsorb onto top of the substrate, and how concentration depends on solubility and vapor pressure that are the gases that are used. And then we have another variant called plasma enhanced chemical vapor deposition, in which case this is a kind of equipment or this is how the chamber looks. You don't need very high temperature furnaces for this, because plasma itself can uh, is the trigger. The stimulus is plasma, it's not temperature here. And the chamber should be at least pumped down to a few millitorr. You need to have the chamber filled with required gas, and pressure and gas flow should be allowed so that it's all stable, and pressure can, and these can vary from few millitorr to few torr. You apply high voltage between the electrodes, and then this ionize the gas molecules. This ionization is responsible for the molecules of the source gas becoming more reactive. These molecules form a thin layer, forming a thin film. And next comes pulsed laser deposition. Again, we need very high pressures, very high vacuum levels inside a pulsed laser deposition system. So what pulsed laser deposition does is, you have a source material which is extremely pure, that's your target, and you have a substrate which is kept exactly opposite to that, and you send pulse lasers of very high powers. Usually these lasers you cannot see, and they should be sent via a quartz window. There's support for that. And once laser beam of such very high power, laser beam of very high repetition rate, which means you're sending pulses, extremely short pulses, this can actually physically knock off the atom because of the local heating of the laser beam, and that forms a plume. This is called a plume, and this comes and hits your substrate. This plume has the atoms of the target material which comes and gets which come and get deposited on top of the substrate, thereby for allowing you to form very highly directional, highly oriented thin films. And the target should be rotating, because you don't want to have the laser beam totally eroding your target. If it is continuously moving, then the laser removal of the target will be uniform. Otherwise, you will have dents and valleys, hills and valleys, which is not a desired form to form the film. Some of the factors that influence the deposition rate in PLD is your target material, the laser energy, the pulse rate or the repetition rate in which the pulses are sent, and then the temperature of the substrate. You can actually also vary the atmosphere inside. You can vary the temperature, you can vary the distance, and you can also vary the type of gas and kind of pressure inside the chamber. So to review, we have seen instrumentation and little basics of the deposition systems to develop thin films. Next is, once you have thin films that are deposited on top of, say, substrates, say you have a silicon nitride deposited by CVD on top of silicon, what we need to do if you want to develop a cantilever or a fixed beam is to pattern it. Patterning is of two types. You have direct methods of transferring the pattern, and then you have indirect methods of transferring the pattern. Indirect method, you can directly write on top of the material, which means you can use an AFM tip or laser tip or laser writing, or an ion, with an ion milling you can literally write. But it is like writing, it's a serial process, it takes a lot of time. Or you can just print, which is also nowadays looked at. It's under investigation for fabrication technology. Or you can just take a mold, use a mold and take it out. That's also possible. And then now we have another way of developing patterning the material, which are called indirect methods. You have an indirect writing, which is covered in electron beam lithography, and then you have an indirect printing where you use projection systems like non-contact lithography, which is projection lithography, and a contact lithography, which is, both of these use UV or laser, so it's also called optical lithography. In terms of CMOS compatibility, optical lithography is highly preferred, except that when you have fine feature, so this is resolution limited, which means you can't use this technique to draw fine features of say few tens of nanometers or few hundreds of nanometer. Even few hundreds of nanometer is possible, but few tens of nanometer is not possible with optical lithographic systems. That's why to develop fine features, extremely fine features, people go for electron beam lithography, but the product associated, the expense associated with it is very expensive, and for a manufacturing industrial types, indirect methods are not even looked at, though to some extent optical lithography is preferred. So if you look at direct patterning versus indirect patterning is straightforward. You have a design, you just write it. It's a physical process, and the resolution is limited by the tip or the scriber that is used to pattern it. And with respect to indirect patterning, it's a resource intense process. Why? Because I'll show you in this figure, you need an intermediate layer in order to transfer the pattern, and then it has to be transferred into the wafer, silicon wafer or silicon nitride wafer that you have. So it involves multiple steps. In terms of flexibility and reproducibility, because it involves multiple steps, it's a little complicated, and because of the same reason it's resource intense. But the kind of features that it gives you to, it's very good. This is how a typical scribing would be probably. It's like an AFM tip writing on top of it, direct writing, direct patterning. So this is what is explained here. You have direct writing, direct patterning, scribing the desired pattern on the wafer like this. You can use ion beam, and it just directly touches the substrate. It's really not good because it can also damage the whole pattern as well as the substrate which is being used. Whereas in indirect patterning, you use an intermediate layer like a polymer, and then use another way to pattern it. It's complicated, but it doesn't damage the sample. It rather gives a very fine feature. In direct patterning, we have ion beam milling, laser writing of polymers, scanning probe lithography, and in indirect patterning, you have optical lithography, e-beam lithography, and nano imprint lithography. This is how a typical process flows. So starting from a wafer, you have to you have to bake it after cleaning, and then baking it has to be heated at say roughly 100 degrees Celsius for 2 minutes or 1 minute depending on the process, and then it has to be cooled down, and then you need to make sure that it has the material that you're going to put on top of it is compatible enough, that is it is adhesive. And then we have to coat a resist, which is typically a polymer which is sensitive to light. We are only discussing optical lithography or the two contact lithography here, which I will come to in detail now. We have a resist, which is a photosensitive polymer, and then it has to be spin coated. The spin coating will tell you how uniform. You need to make sure that it is very uniform and it does not spill over the sides, and it is spread across this entire substrate uniformly. And then once it is coated, we need to soft bake it, which means it has to be, before exposure it has to be slightly baked, and then it has to be cooled, and then it has to be exposed to the UV light that we are talking. Again, it has to be cooled down. Then it has to go through another exposure. After exposure, it has to go through another baking. After that, it has to be cooled. And then, like yesterday's developing photos, this also has to be developed. And once developed, what it does is it forms a pattern, temporary pattern on top of the substrate. Then now that has to be cleaned. In the sense the pattern has to survive and the rest of the things have to be cleaned, and then it has to go through a dehydration bake, cool down, and the wafer is out. So in lithography, It's a process where light is used to print or pattern the surface of a substrate, metal or a dielectric, with devices, interconnections and structures which are very complex and which can be multi-layered also. And lithography is basically two types of lithography are there. One is photolithography, another one is electron beam lithography. We will deal with photolithography here now. And it's usually complex and requires different layers of materials to be patterned. The typical transfer happens like this. Initially you have a substrate and then you are coating a photosensitive material on top of the substrate, and then after spinning, this is where spin coating comes, which we have not discussed in the thin film deposition. The spin coating comes here, and we make sure that the spin coating is perfect, that the resist is coated uniformly across the substrate, and then it has to be baked to remove off the extra solvents. It has to be heated, and then we have a mask, which is if it is kept at a farther distance, then we use Fraunhofer diffraction, which is projection for the photolithography. But mostly we here after this slide I'll be talking about contact lithography. We'll be only dealing with the masks which are in proximity, kept in proximity to the substrate. And so we have a pattern here. The mask has a pattern, and once you expose it UV light, this forms a pattern over your there is a reaction between light and the layer here, and after this is transforming, this is transferring the pattern, and then this has to be taken through etching. This is a broad overview of how the entire process is. It has to be taken through etching. Either it can be dry or wet, and when you do etching you also expose the next layer, and what now happens is the substrate itself has the pattern when you remove off the resist or the soft material. So again, this is how typically it happens. You have a photosensitive material, which is a polymer, which is also called a photoresist. When exposed to UV, it reacts, and the exposed section is now removed. And now what you have is only if it is removed, it is positive photoresist. If the unexposed section is removed after developing, it's called negative photoresist. Now this explains the process of say contact photolithography. Here you have a wafer, and then you want, this is a silicon wafer, and you want a particular structure to be deposited on top of this. So what you do, you only have the wafer, and now you use this design, which is called a photo mask. So the design is done by the user, and it is given to a vendor who actually makes a mask and gives it back to us. The photo mask is typically a material made of quartz or glass, and the material that is deposited here is a metal here, so which doesn't allow light to pass, and it blocks its opaque region. Now when you place this on top of the substrate and this is a metal pattern, and allow UV to fall on top of it, it forms the pattern like this. But before that, we need to also coat the photoresist and then place the mask, and when you shine light on top of it, the areas that are exposed here are going to go off, leaving behind only the pattern here. And this further has to be taken through, after developing it will look like this, and this has to be taken through different levels of etching in order to get just the silicon with the metal on top of it. And after this etching process, the photoresist will be removed. This is how masks look. You have a quartz or a glass layer predominantly, and you have fine patterns which are marked here. They have very complicated patterns inside if you look down deep. And that's the regions where like cannot, it is opaque. So a typical process in order to make sure that it is understood correct, we start with spin coating of photoresist on top of a substrate. The substrate is say 200 to 600 micron thick, and you have a photoresist of 1 to 20 micron thick, and the photoresist or the thickness, all these things depend on the kind of process we need, the kind of dosage that we use, and it is the kinetics of photoresist. All of these play a huge role. It all depends on the kind of devices, thickness, features, everything. So accordingly, these combinations should be chosen. And then you have, a mask, UV light hitting the mask. Only those regions that are around the metal is intact, the other things are exposed, and this is the exposed area. Once you develop it, this is how it's going to be. You have photoresist here, the other ones are exposed, and it has to be developed. It has to be put in a petri dish with a developer, which is also a chemical. You need to have the right chemical for the right photoresist, and it is like photo development that is used once upon a time. And after this, if every region is clean, you only have the wafer, on top of it the photoresist, and this has to be after etching. You only have, after say chemical wet etching, you only have the substrate and the gold on top of it, and this has to be cleaned, and nitrogen should be blown after this. Next comes the idea of process of etching. Etching can be both wet etching and dry etching. You need to make sure you have suspended, suppose you have fixed beams, suspended structures, you need to make sure that the undercutting is done well, which means the structures should be suspended, which means even the silicon substrate should be removed underneath the pattern, and there are advantages, disadvantages. The advantages, you deal directly with these chemicals, and these chemicals in wet etching can be strong acids and bases, which is disadvantage. And advantage is very selective. It forms isotropic etch form, and what really happens is in a wet etch, if you use hydrofluoric acid, you have the material silicon dioxide. Suppose you have a silicon dioxide to be removed, it forms this, and it is easily removed. It's no more silica. And sometimes, in order to expedite, increase the rate of this reaction, buffering agents like ammonium fluoride are used. So there has to be combinations of materials and combination of etchants. Randomly things cannot be used, and these are chosen for a particular, say, photoresist. Similarly, you have dry etching. You have it also needs very vacuum systems, and you place your substrate, which is already patterned and developed, and this substrate is placed between the electrodes here, and some gases, desired gases, are flown here. Dry etch can be both physical and chemical. A combination of both gives the best results. And when a high voltage is applied between the two electrodes, it forms plasma. In the wet etch, you have both the sides of the substrates are exposed to the etching. Here only one side of the substrate is exposed to the etching, the other side faces the electrode. When high plasma is created, you have both chemical and physical processes happening. Suppose you use a fluorine chemistry, CF4 chemistry. This plasma gives rise to CF3 and F, and this fluorine is going to see your silicon, which is say you have prepared a silicon nitride cantilever, and you have silicon underneath a substrate, and you don't need silicon, and you only need silicon nitride cantilever underneath. It has to be hanging underneath. Silicon can be removed when it reacts with, say, this F free radical, and then it forms Si4, which can be easily removed from the chamber. That gives rise to a very nice film. It also has both its advantages and disadvantages. Finally, as I have taken you through a steps of fabrication, deposition, vacuum, and fabrication system processes, here are some of the beams that I have made, fabricated. You can see them here. There is nothing here. There is no beam here. It is all dead. Same is the case here. There are no beams. Whereas if you look at these fixed beams, you have a nice beam over here of different dimensions. So this was taken through silicon nitride chemical vapor deposition, followed by patterning with our design. We have made this design and written it with UV lithography, followed by set of etching for different exposure times, different recipes, and then this has to be validated all the time. So before and after, what dimensions we desired, what dimensions we started off with, whether we are able to get the same dimensions back or the desired dimensions back, for which we need to do optical profilometry, step size detection, as well as the feature size detection from optical micrographs, microscope, and then finally an electron microscope image to see the structures that we have made. Thank you. If you have any doubts, please let me know. Thank you for your patience. Thank you so much.